This is a sample problem
We're going to talk about the
sample calculation. We're going to find power.
The Amsar's video for section 4
As the drawing shows, the support cable
Now, one thing that people get confused about is the difference between the surface area and cross-sectional area. So, as an example, I thought I would look at a cylinder.
And in 20 seconds, I might
find the tension in the support cable and the magnitude of the force applied on the lower end of the
Let's compare the surface area with the cross-sectional area. So first of all, if I look at the surface area of the solid, it actually has 3 surfaces. So what I'm going to do is add the area of all 3 surfaces together. There are 2 ends, and then there's the curved part. So the area of each end is going to be pi r squared, which is the area of a circle. Then I need to add to that the area of the curved part. The way you can think of that is to think of the circumference of a circle, and then stretching that circumference down the length of the cylinder. So the circumference of the circle is 2 pi r. Multiply that by the length of the cylinder. Now what I want to do is simplify this as much as possible. I'll give the surface area the symbol A. I add the 2 areas of the ends together, 2 pi r squared.
The wrecking ball has a weight, W sub L.
And then, to make this easier to use, I'm going to factor all the common terms out. Here's the factor. 2 times pi times the radius, and what's left is the radius of length. So that would be the area of the surface of the cylinder. And that area is the boundary between the object and the cylinder and its environment. Now, if I take that cylinder and slice through it, then I would be measuring cross-sectional area. So imagine that this is the and I take a knife and I cut through it. Let's say I cut through it this way, chop right down through the middle. And when I do that, I get smaller cylinders.
Equilibrium has 2 requirements.
So the cross-sectional area would be the new areas that's exposed. Now really, in this case, there are 2 of those. I'm not going to double count them. I'm just going to count them once.
I could do better.
So the cross-sectional area, if I slice it perpendicular to the length, then that cross-sectional area is just the area of the circle. And again, I'm not going to double count. Just one of them. So the cross-sectional area would be pi r squared. You can see that's different than the surface area. Unfortunately, a lot of times we use the same symbol for area. So you have to know from the context what the symbol is for, surface area or cross-sectional. Now what would happen if we took the same
that the angle between the balloon and the tension is equal to psi times theta.
We've got the package all the way over there at 17 millimeters, and now we're going to move it to the other
Some of
side
the
of the
horizontal
zero
force
mark.
components is
That's
shown here.
So
The horizontal
cut through it like that, let's
component
say
of the force on the
exactly
hinge minus the horizontal component of the torsion
the
force.
surface that will be exposed.
Let's solve this
If
equation
I look at it from the top,
In this
would be a
equation,
rectangle.
we know the value of theta, but the magnitude of the tension is
Going to
the
be
parameter to
work
be
is
found
equal
for
to
part A.
work done by the spring is going to be equal to
Similarly, we
So
find
the
the sum of the
cross-sectional area
forces in
depends
the
on how
y
you
direction.
slice it, which
The
way
component V is
cut
the
the
only
object.
one directed upwards,
So
while
in
the
this
2
case,
weights,
we're going to
we
put
get
the
a
numbers in
vertical
rectangle.
initial
and
position this time
Look,
are directed downward.
17.
that's just a
why
long
we're
way
doing
of writing out a dot
We solve
product.
this equation for
And
V.
then
The dot
on the
product
side,
is
that's the diameter of
In
the circle,
equation
which
2,
is the same
we know the
as
value
force
of the
vector
force
dotted
and the angle
the
theta.
velocity vector
But again,
r
the
So in this
magnitude
case,
of the tension
cut it
force is unknown.
in this direction.
on a dot product.
The
The
cross-sectional
components V
area
and H
Positive
can be used to find the
This
magnitude
is
of
another
the
way
force
that I
F sub
would
P
write
by
down
using equation 3.
And if I wanted to express that in terms of radius,
At this point, we have
the
three
diameter
unknowns,
is
done, and this
but
time
only
twice
two
the
equations.
positive.
A third equation is
give you
the
a
cross-sectional area would be
It is
2 times the radius
equation for the
times the
sum of
length.
the chords.
Package
This
out
will be as
angle
So it's
well.
important to
phi
recognize
is
the difference between
the spring did
surface area and
negative work.
cross-sectional
We
area.
did
This will become
positive
very
work.
important later
There's
on
the
when
F
we
vector.
start talking
Here is a
about
hint on how to find the
how
magnitude of the
energy
tension
moves
T
from one
and the
place to
force
another
T
because of
is
temperature
F
difference.
C.
package
I will have the
Kind of
most
energy
To write the
power
torque equation, it is helpful to put
And
the
the amount of future
indication
flow
axis to
angle on
opposite
in various
here
cases will depend on
is now going to be
This will result in a
small
sum of
amount
torques
of
equation
negative
that will
work.
So
enable
it's a
you
good idea
to
to
solve for T
distinguish
in terms of the known
zero
variables.
to
zero with
Be sure to
negative
find the
1.
correct
And I
lever
recommend
arm
you go through
for
the
each
same
force
procedure
acting
for
on
other
the
Large
shapes.
amount of positive
What do I
work.
get if
spheres.
I
After finding T,
You
we use
at
its
an
value
angle
in
of
equations
like
1
that.
and 2.
9 degrees?
Then it'll
Once
be
you have the
easy to
components of
move
F
around.
sub T,
So go
how
ahead
you
and
can
try
then
that out.
complete the solution.
And now
And we'll
I'm
see
pulling
you later on.
upward, not enough to lift the block. It's still sliding across the floor. Can you see that this is, shall we coin a phrase, stupid? Because if I put in 90 degrees right there, cosine of 90 is 0. I'm pulling up for nothing. The power that I'm using to move the block is 0. I may be straining muscles, but I'm not going to be making the block go faster or slower. Now, for 0 degrees, I had the most power I could get with the given amount of force, and so I would be making the block go faster and faster and faster. I'm adding energy to the block. I'm adding nothing, no energy to the block here. And one more case, block's still sliding to the right, but I'm pulling to the left. So the angle between the displacement vector, still x to the right, and the F vector, well, that's going to be 180 degrees. Can you see that when I put this in, I get -1? I will be removing energy from the block. I'll be making it go slower and slower. The power that I'm applying to the block is now a negative number because I'm taking energy away. Let's do a little quick summary of ideas here. Power is the ratio of work to time. Average power, you're averaging the amount of work being done over a time interval, 30 seconds, an hour, a day, something like that. But you could be worried about the power at a given instant, instantaneous power. That's the rate at which work is being done just then. We can also write power, the instantaneous power, as the dot product of the applied force and the velocity of the object just then. And this is the way we can expand the dot product, magnitude of F, magnitude of V, cosine of the angle between those two vectors and the dot product. And that's it for this little video.